Have you ever stopped to consider the invisible forces that hold our universe together? We gaze up at the night sky, marveling at the stars and galaxies, but what we can't see may be even more extraordinary. Hidden throughout the cosmos are magnetic fields of such immense power. They defy our understanding of physics and reality itself. These are not the gentle magnets you played with as a child. These are cosmic monsters, capable of twisting space-time, shredding atoms, and creating environments so extreme that they challenge everything we thought we knew about the laws of nature. Today, we're embarking on a journey to explore the most extreme magnetic fields in the universe, forces so powerful they can stretch across light years, influence the birth and death of stars, and even warp the very fabric of existence. Imagine a magnet so strong that if you were to bring a credit card within 1,000 kilometers of it, the magnetic force would literally rip the card apart, atom by atom. Or consider a star with a magnetic field billions of times more powerful than Earth's, a field so intense it can squeeze matter into forms denser than anything we've ever created. These are not just theoretical curiosities. They are real, dynamic forces actively sculpting the cosmos around us. From the mysterious magnetars whose eruptions can be felt across the galaxy, to the vast magnetic webs that guide the formation of entire galaxies, these invisible architects are perpetually at work, driving some of the most spectacular and violent events in the universe. What makes this exploration so thrilling is that we are only just beginning to understand the full scope of these magnetic extremes. With every new discovery, we peel back another layer of the cosmic onion, revealing realities that are stranger and more magnificent than we ever imagined. This video will guide you through 30 astonishing facts about these incredible forces, each one a testament to the universe's boundless creativity and power. So settle in, open your mind to the wonders waiting just beyond our perception, and prepare to see the cosmos in a whole new light. The journey into the heart of magnetic extremes starts now. Our journey into cosmic magnetic extremes begins with the undisputed champions of magnetic force, the Magnetars. To even begin grasping their power, we first need to redefine our understanding of what a magnet can be. Forget the small one holding a shopping list to your refrigerator. We're talking about a force so fundamentally powerful it warps the very building blocks of reality. A magnetar is a specific type of neutron star, itself the incredibly dense, collapsed core of a massive star that died in a supernova explosion. But a magnetar takes that natural intensity and magnifies it to an almost incomprehensible degree. These objects possess magnetic fields that are a staggering quadrillion times stronger than Earth's protective magnetic shield. To put a number on that, it's a 1 followed by 15 zeros. The creation of such a monstrous object is as violent as you might expect. It starts with the death of a star. When a star significantly more massive than our Sun exhausts its nuclear fuel, its core collapses under its own immense gravity. This collapse triggers a cataclysmic supernova explosion, blasting the star's outer layers into space. What remains is a neutron star, an object so dense that a single teaspoon of its material would weigh billions of tons. Now, for a magnetar to form, this collapsing core needs to be spinning extremely rapidly. Think of an ice skater pulling their arms in to spin faster. The same principle applies here on a cosmic scale. As the star's core collapses, its rotation speeds up dramatically. This combination of rapid spin and the incredibly dense, fluid interior of the newborn neutron star acts like a gigantic dynamo, amplifying a pre-existing magnetic field to those mind-boggling levels. The magnetic field of a magnetar isn't just strong, it fundamentally alters the environment around it. It's so intense that it can actually distort the shape of atoms themselves. In a field of this magnitude, an atom, which we normally picture as a spherical cloud of electrons orbiting a nucleus, gets stretched into an elongated, thin, cigar-like shape. The electrons are forced to move only along the magnetic field lines, completely changing how chemistry and physics operate in its vicinity. This is a place where the rules of our everyday world cease to apply, governed instead by the sheer, overwhelming power of magnetism. Now, to even begin talking about the power of a magnetar, we first need a common language, a way to measure these invisible forces. In our daily lives, we might describe a magnet as strong or weak, but scientists require precise numbers. For magnetism, that precision comes in two main units, the Gauss and the Tesla. You can think of them like miles and kilometers. They both measure distance, just on a different scale. A Tesla is actually equal to 10,000 Gauss, making it the larger, more powerful unit. This scale gives us a ruler against which we can place everything from the most mundane magnet to the most terrifying cosmic entity. To anchor ourselves, let's start at the very bottom of this scale with a field we all live within, Earth's own magnetic field. This planetary shield, which protects us from harmful solar radiation and guides compass needles, measures a relatively gentle 0.3 to 0.6 Gauss. That's only about 30 to 60 millionths of a single Tesla. It's a vital force, but a faint one in the grand scheme of magnetism. Now walk to your kitchen. That small magnet holding your child's drawing to the refrigerator, that's significantly stronger, typically registering around 50 Gauss. It's powerful enough for its job, but still utterly insignificant compared to what's out there in the cosmos. This is where our scale truly explodes. A run-of-the-mill neutron star, which is already one of the densest objects in the universe, can possess a magnetic field measuring 1 trillion Gauss. That's a 1 with 12 zeros after it. That number is so large it becomes almost meaningless to us, but remember, that's just a regular neutron star. We are here to talk about the extremes. A magnetar's field operates on a whole other level, typically measuring around 1 quadrillion Gauss. If we convert that to Teslas, we're looking at 100 billion Teslas. Let's try to frame that power in a more tangible and frankly horrifying way. If a human astronaut were to unfortunately find themselves just 1,000 kilometers away from a magnetar, something truly science fiction would happen. The magnetic field would be so intensely powerful that it would begin to affect the very atoms that make up that person's body. It wouldn't just pull on the iron in their blood, it would distort the electron clouds surrounding every single atom. The chemical bonds holding their molecules together would simply cease to function as we know them. Matter itself would be reorganized by the sheer force of the magnetic field. This is the scale we are dealing with. It's not just about moving metal objects, it's about controlling the fundamental rules of physics in its vicinity. With this immense scale in mind, from a fraction of a Gauss on Earth to quadrillions of Gauss in deep space, we can now properly appreciate the staggering facts to come. But how does a star, or even a planet like our own Earth, generate such a powerful, persistent magnetic field in the first place? The secret lies in a process happening deep within their cores, a brilliant piece of cosmic machinery known as the dynamo effect. To understand this, we need to think of these celestial bodies not as solid, silent rocks, but as dynamic, churning power plants. The core ingredient for a dynamo is a rotating, convecting, and electrically conductive fluid. On Earth, that fluid is primarily molten iron swirling within our planet's outer core. In a star, it's a searing plasma of ionized gas. The process begins with motion. This conductive fluid is in constant motion for two main reasons: rotation and heat. The entire planet or star is spinning, and that spin drags the fluid along with it. At the same time, the incredible heat rising from the very center of the object causes this fluid to churn in massive convection currents, much like water boiling in a pot. Hot material, being less dense, rises toward the surface. As it rises, it cools down, becomes denser, and then sinks back down again, creating a continuous, turbulent loop. Now here's where the magic happens. Let's say there's a tiny, pre-existing magnetic field present. This could be from some ancient, faint background field. As this electrically conductive fluid moves through that weak magnetic field, it acts like a copper wire moving past a magnet. This motion induces an electrical current to flow within the fluid itself. And as any student of basic physics knows, an electrical current, in turn, generates its own magnetic field. This newly created magnetic field is then stretched, twisted, and amplified by the complex churning motion of the fluid. The rotation of the body organizes this chaos, wrapping the magnetic field lines around the axis of spin and turning them into a coherent, large-scale global field. It's a self-sustaining feedback loop. Motion through a magnetic field creates electric current, which creates a stronger magnetic field, which induces more current, and so on. This cycle continues to amplify the field until it reaches a stable, immense strength. This dynamo effect is remarkably universal. It explains not only Earth's protective magnetic shield, but also the Sun's powerful field, which drives the solar cycle of sunspots and flares. And it's the very same principle, pushed to its absolute extreme, that creates the monster fields of a magnetar. During the violent collapse of a massive star's core, you have the perfect, terrifying storm for a super dynamo, an unimaginably dense fluid of neutrons and protons, spinning at a significant fraction of the speed of light and churning with ferocious convection. This amplifies a standard neutron star's already immense field into the magnetar's quadrillion Gauss powerhouse, turning the interior of a dead star into the most powerful magnet in the known universe. While the magnetic fields of distant magnetars are almost beyond human comprehension, we don't have to look far into space to witness the raw power of magnetism in action. In fact, we have a spectacular and sometimes disruptive demonstration happening right in our own celestial backyard, powered by our very own star. The sun may seem like a steady, glowing orb, but its surface is a seething, dynamic canvas of magnetic violence, and the most visible signs of this are sunspots. These dark blemishes on the solar surface are far more than just cool spots. They are the footprints of immensely powerful, concentrated magnetic fields bursting through the sun's photosphere. A sunspot forms when the sun's internal dynamo, that churning engine of plasma we discussed, gets tangled and twisted. The sun doesn't rotate as a solid ball. Its equator spins faster than its poles. This differential rotation stretches and wraps the magnetic field lines beneath the surface over time, like winding up a rubber band. Eventually, these strained magnetic fields can kink and erupt through the solar surface in great loops. Where these powerful magnetic field lines punch through, they effectively put the brakes on the convection process, the rising and falling of hot gas that normally brings heat to the surface. This inhibition of heat flow causes that area to cool down significantly, from the sun's usual surface temperature of around 5,500 degrees Celsius to about 3,500 degrees. That's why they appear dark to us. They are cooler and therefore emit less light compared to the brighter, hotter surrounding regions. But the darkness is a deception. It belies the incredible energy contained within. The magnetic field strength in a typical sunspot is immense, measuring around 3,000 Gauss. To put that in perspective, that's roughly 3,000 times stronger than Earth's magnetic field, and over 100 times stronger than a common refrigerator magnet, all concentrated into an area that can be larger than our entire planet. This concentrated magnetic energy doesn't just sit there quietly. These regions are incredibly unstable, storing colossal amounts of energy that the sun desperately wants to release. When the tension in these twisted magnetic fields becomes too great, they can suddenly and catastrophically reconfigure themselves in a process called magnetic reconnection. It's like cutting a massively overstretched rubber band. The snap releases all the pent-up energy at once. This explosive release of energy manifests in two primary ways, both of which have direct consequences for us here on Earth. The first is a solar flare, a sudden and intense flash of radiation across the entire electromagnetic spectrum, from radio waves to gamma rays. A single large flare can release more energy than 1 billion megatons of TNT, all in a matter of minutes. This burst of radiation travels at the speed of light, reaching Earth in just over 8 minutes. While our atmosphere protects us on the ground from the worst effects, this radiation can be hazardous to astronauts in space and can cause significant disruptions to radio communications and GPS signals. The second, and often more impactful, event is a coronal mass ejection, or CME. This is when the Sun hurls a massive cloud of superheated plasma electrons and protons directly into space, embedded within its own magnetic field. These billion-ton clouds can travel at millions of miles per hour. If a CME is aimed at Earth, the effects can be dramatic. When this magnetized cloud slams into our planet's protective magnetic field, it compresses it and transfers energy into it, triggering a geomagnetic storm. The most visible effect of such a storm is the aurora borealis and aurora australis, the northern and southern lights, as charged particles are funneled by Earth's magnetic field toward the poles and collide with atoms in our atmosphere, causing them to glow in beautiful, dancing curtains of light. But the beauty comes with a potential for disruption. A powerful geomagnetic storm can induce massive electrical currents in long conductors on Earth, such as power grids and pipelines. The most famous example is the Carrington event of 1859, a solar superstorm so powerful that telegraph systems, the advanced technology of the day, failed across Europe and North America, with operators receiving shocks and some telegraph papers even catching fire. A storm of that magnitude today, in our utterly electricity-dependent world, could cause widespread and long-lasting blackouts, damaging critical transformers and crippling satellites we rely on for everything from navigation to banking. So, while sunspots may look like tiny, dark specks on a distant star, they are in fact the source of solar storms that serve as a potent reminder of our intimate and sometimes vulnerable connection to the magnetic fury of our Sun. But our solar system's magnetic drama isn't confined to the Sun's explosive surface. For a truly planetary scale display of invisible power, we must turn our gaze to the solar system's giant, a world so massive it commands its own miniature cosmic neighborhood, Jupiter. This gas giant doesn't just have a magnetic field, it possesses a magnetic fortress of such staggering proportions that it fundamentally reshapes the space around it. In fact, Jupiter's magnetic field is the strongest of any planet in our solar system, a colossal force roughly 20,000 times more powerful than the one that protects our own planet Earth. To understand the sheer scale of this force, we need to look inside the planet itself. While Earth's dynamo is powered by molten iron, Jupiter's engine is fueled by something far more exotic, metallic hydrogen. Deep within Jupiter's immense interior, the pressure from the overwhelming weight of its atmosphere becomes so astronomically high that it compresses the most basic element, hydrogen, into a bizarre, fluid metallic form. This metallic hydrogen, swirling at temperatures of thousands of degrees and under millions of times the pressure we experience on Earth's surface, is a superb electrical conductor. Combined with Jupiter's incredibly rapid rotation, a day on Jupiter is a mere 10 hours long. This creates the most powerful planetary dynamo known. The churning of this conductive ocean generates a magnetic field that is not only immensely strong but also incredibly vast. This magnetic power extends outward from the planet, carving out an enormous protective bubble in the solar wind known as a magnetosphere. If you could see Jupiter's magnetosphere from the side, it would appear as a gigantic teardrop shape stretching away from the Sun. It is so unimaginably large that even at its minimum size, it is still wider than the Sun itself. To put that in perspective, if our eyes could perceive magnetic fields, Jupiter's magnetosphere would appear larger in our night sky than the full moon, a glowing, shimmering dome of energy dominating the heavens. This is the true footprint of its magnetic dominance. Within this gargantuan magnetic fortress, Jupiter traps and accelerates charged particles, mostly electrons and protons, swept up from the solar wind and blasted into space by its violently volcanic moon, Io. These particles become trapped, whirling around the magnetic field lines at nearly the speed of light, creating zones of intense radiation that are thousands of times more powerful than Earth's Van Allen belts. This radiation is so ferociously lethal that it poses an existential threat to any spacecraft that dares to venture too close for too long. NASA's Juno spacecraft, which has been studying Jupiter since 2016, had to be equipped with a titanium vault to shield its sensitive electronics from this relentless planet-sized particle accelerator. Even with this protection, Juno's mission is carefully designed to avoid the most intense radiation regions, dipping in for quick data collection before retreating to a safer orbit. The most spectacular visual evidence of this magnetic power isn't the radiation itself, of course, but the breathtaking auroras it creates at Jupiter's poles. Because the planet's magnetic field is so strong and gathers so many particles, the auroras there are permanent, raging rings of light hundreds of times more energetic than their earthly counterparts. They are colossal, continuous storms of light, big enough to engulf our entire planet, shining in ultraviolet and other wavelengths with a brilliance that is both beautiful and terrifying, a constant testament to the invisible, energetic titan we call Jupiter. While Jupiter's magnetic field is a planetary titan, the universe holds even more precise and rhythmic magnetic wonders. If a magnetar is the universe's ultimate powerlifter, then a pulsar is its most disciplined and reliable timekeeper. These objects are a specific, mesmerizing type of neutron star, and they demonstrate another incredible application of extreme magnetism, not for raw destruction, but for creating the most accurate clocks in the cosmos. The story of their discovery is almost as fascinating as the objects themselves. Back in 1967, a young graduate student named Jocelyn Bell Burnell was analyzing data from a radio telescope when she noticed a peculiar repeating signal. It was so perfectly regular, a pulse of radio waves arriving every 1.337 seconds with breathtaking precision, that she and her supervisor half-jokingly dubbed it LGM for Little Green Men, entertaining the possibility it was a beacon from an advanced civilization. What she had actually found was the first known pulsar, later named CP1919, and it opened an entirely new window into the most bizarre states of matter in the universe. So, what exactly is a pulsar? At its heart, it is a neutron star, the incredibly dense remnant of a supernova explosion, but with two very special characteristics. It is spinning incredibly fast, and it has a highly focused, powerful magnetic field. Unlike a magnetar, whose magnetic field is mind-bogglingly strong but often chaotic, a pulsar's field is more organized and channeled. This magnetic field does not align with the star's rotational axis. It's tilted, much like the magnetic field of Earth is offset from its geographic poles. Because the magnetic field is so intense, it rips charged particles from the surface of the neutron star and accelerates them to nearly the speed of light. These particles race along the magnetic field lines, and as they curve around at the magnetic poles, they emit powerful beams of radiation across the entire electromagnetic spectrum, from radio waves to gamma rays. This is where the lighthouse effect comes in. Imagine a lighthouse on a foggy coast. The lamp itself is always on, but to a ship at sea, it appears to flash only when the rotating beam sweeps directly across its line of sight. A pulsar operates on the exact same principle. The beams of radiation are RE Chinese letter from the magnetic poles. As the neutron star rotates sometimes hundreds of times per second, these beams sweep through space. If Earth happens to lie in the path of one of those sweeping beams, we detect a very brief, incredibly regular pulse of energy with every rotation. The timing of these pulses is unbelievably stable, rivaling the precision of atomic clocks. This is why they are called cosmic lighthouses. We only see them flash because we are in the right place at the right time to be illuminated by their spinning beam. This incredible precision makes pulsars far more than just celestial curiosities. They are practical tools for navigation on an interstellar scale. Think about how we navigate in deep space. We can't use GPS, which is reliant on satellites orbiting Earth. Instead, we use a technique called pulsar timing. Because each pulsar has its own unique rotation period and is located in a fixed position in the galaxy, they form a kind of galactic positioning system. By measuring the precise arrival times of pulses from several known pulsars spread across the sky, a spacecraft could theoretically triangulate its position anywhere in the galaxy with an accuracy of a few kilometers. NASA has already experimented with this concept. The Voyager probes carry plaques with a pulsar map pointing back to our solar system, and the SEXT-NT project is actively developing technology to use pulsars for real-time navigation on future crewed missions to Mars and beyond. We are essentially using the steady, reliable heartbeat of dead stars to find our way through the vast ocean of space. The stability of a pulsar's pulse is a direct testament to the incredible density and rigidity of a neutron star. There is simply nothing in our everyday experience that can compare to its solidity. A typical pulsar, packing more mass than our Sun into a sphere the size of a city, rotates dozens or even hundreds of times every single second without flying apart. The pulse period can be measured and predicted with microsecond accuracy over decades. However, these cosmic clocks are not entirely perfect. Occasionally, a pulsar will experience what astronomers call a glitch, a sudden, tiny increase in its spin rate. These events are tremendously exciting for scientists because they provide a rare glimpse into the exotic interior of a neutron star. A glitch is thought to occur when the superfluid core of the neutron star, which normally rotates smoothly, suddenly transfers angular momentum to the more rigid outer crust, giving it a brief speed up. It's a tiny stellar earthquake that reveals the complex and bizarre physics at work within. From their almost magical discovery to their application as the universe's most reliable navigational beacons, pulsars stand as a brilliant example of how extreme magnetism, when combined with rapid rotation, can create some of the most useful and predictable phenomena in the entire cosmos. Yet for all their structured power, these magnetic fields are not always stable. They can store immense energy like a coiled spring, and when they finally release it, they do so in one of the most fundamental and violent processes in the universe, magnetic reconnection. This phenomenon is the master key behind some of the most energetic events we observe, from solar flares that burst from our sun to the magnificent auroras that dance over our poles. At its heart, magnetic reconnection is a simple concept with cataclysmic consequences. It occurs when magnetic field lines, which are normally locked in a stable configuration, are pushed together, break, and then reform into a new, lower energy arrangement. Think of it like crossing two rubber bands and stretching them taut. They push against each other, storing elastic energy. If you were to suddenly cut them, the tension would be released in a snap as the ends fly apart. Magnetic reconnection is the cosmic equivalent of that snap, but on an almost unimaginable scale. The energy released in this process is truly astronomical. It comes from the magnetic field itself, which is a form of stored energy. When the field lines break and reconnect, a portion of that stored energy is converted almost instantly into heat and kinetic energy, violently heating plasma and accelerating particles to nearly the speed of light. This is the engine that powers a solar flare, capable of releasing more energy than 1 billion megaton nuclear bombs in a matter of minutes. It's not an explosion in the sense of burning fuel. It is a fundamental restructuring of the magnetic landscape, and the energy difference is what we witness as a cataclysm. We see the effects of this process most clearly in our own solar system. The Sun's surface is a constant ballet of magnetic fields rising, twisting, and tangling. When the stress becomes too great, reconnection occurs and we see the brilliant flash of a flare. But the effects don't stop there. Often, this reconnection event can also propel a colossal cloud of solar material, a coronal mass ejection, out into space. If aimed at Earth, this magnetized cloud travels for days before colliding with our planet's protective magnetic shield, our magnetosphere. And what happens during this collision? More magnetic reconnection. The magnetic field embedded within the solar cloud interacts with Earth's own field lines. They break and reconnect on the side of Earth facing away from the Sun, transferring energy into our magnetosphere and funneling charged particles down towards the poles. This influx of particles is what excites atoms in our upper atmosphere, causing them to glow and create the breathtaking auroras. While beautiful, this energy transfer is a potent reminder that we are connected to the Sun's magnetic fury. The same process that paints the sky can also induce powerful electrical currents in the ground. These geomagnetically induced currents can flow through man-made conductors like power grids, pipelines, and railways. Under normal conditions, this is a minor effect, but during an extreme geomagnetic storm, the consequences can be severe. The most famous historical example is the Carrington event of 1859, a solar storm so powerful that telegraph systems across Europe and North America failed spectacularly. Operators received electric shocks, telegraph paper caught fire, and some systems even continued to send and receive messages after being disconnected from their power sources. In our modern, hyper-connected world, a storm of similar magnitude would be catastrophic. It could overload and destroy massive power transformers, leading to widespread, long-lasting blackouts affecting millions. It could disable the satellites we rely on for communication, navigation, and weather forecasting, and disrupt GPS signals essential for everything from aviation to financial transactions. Magnetic reconnection is thus not just an abstract cosmic concept. It is a physical process with a direct and powerful line to our daily technological lives, demonstrating that the universe's most extreme magnetic fields are both a source of sublime beauty and a formidable force to be respected. While the Sun's eruptions and Jupiter's colossal field are awe-inspiring, we are the beneficiaries of a far more personal and vital magnetic phenomenon, our own planet's protective shield. Earth's magnetic field may seem humble in comparison to these cosmic powerhouses, but it is arguably the most important magnetic field we know of, because without it, life as we know it simply would not exist. This invisible force field extends tens of thousands of kilometers into space, acting as a planetary deflector shield against a relentless and deadly barrage from the Sun. The solar wind, a constant supersonic stream of charged particles, mostly electrons and protons, flows outward from the Sun, bathing the entire solar system. If this wind were to strike Earth's atmosphere directly, it would slowly but surely erode it away, stripping away the very air we breathe, much as scientists believe happened to Mars after its magnetic dynamo shut down billions of years ago. But our magnetic field intercepts this onslaught. When the solar wind encounters Earth's magnetic field, something remarkable happens. The charged particles within the wind feel a force, the Lorentz force, that causes them to spiral along the magnetic field lines instead of crashing directly into our atmosphere. The majority of this particle stream is deflected around our planet, flowing harmlessly past us in the solar system's wake. Our magnetic field effectively creates a protective bubble, a region of space known as the magnetosphere, which serves as our first and most important line of defense. However, this defense is not perfect, and the interaction between the solar wind and our magnetosphere creates some of the most fascinating structures in near-Earth space, chief among them the Van Allen radiation belts. Discovered in 1958 by America's first satellite, Explorer 1, the Van Allen belts are two giant, donut-shaped zones of trapped, high-energy charged particles that surround our planet, held in place by Earth's magnetic field. Think of them as enormous particle accelerators naturally formed in the sky. The inner belt is fairly stable, consisting mostly of high-energy protons, and stretches from roughly 600 to 6,000 kilometers above the Earth's surface. The outer belt is more dynamic, populated primarily by electrons, and ranges from about 13,000 to 60,000 kilometers out. These belts are not something we can see or feel, but they are a crucial part of our magnetic environment. They act as a kind of magnetic prison, capturing and storing the most energetic particles that manage to penetrate the outer magnetosphere, preventing them from reaching lower altitudes where they could damage satellites and threaten astronauts. This brings us to the most visually stunning consequence of our magnetic shield being breached, the aurora. While our field does a superb job deflecting the solar wind, some particles do manage to get inside, particularly during periods of heightened solar activity like solar flares and coronal mass ejections. These events send stronger, faster gusts of charged particles toward Earth. When this enhanced solar wind distorts our magnetosphere, it can trigger magnetic reconnection events on the night side of Earth. This process funnels electrons down along the magnetic field lines toward the polar regions. As these electrons scream down into the upper atmosphere, they collide with atoms of oxygen and nitrogen. These collisions transfer energy to the atmospheric atoms, exciting their electrons to higher energy states. When those electrons then fall back to their normal state, they release that energy in the form of light, the shimmering, dancing curtains of green, red, and purple that we know as the aurora borealis and aurora australis. The colors themselves tell a scientific story. The most common green hue comes from oxygen atoms being struck at altitudes around 100 kilometers. Much higher up, above 300 kilometers, rarer collisions with oxygen can produce a deep red glow. Meanwhile, interactions with nitrogen molecules tend to produce bluish or purplish red light. This spectacular light show is more than just beautiful. It is direct, visible proof of our planet's invisible magnetic force field at work, a constant negotiation between the fury of our sun and the protective embrace of Earth's magnetism. It is a delicate balance that has allowed our atmosphere to remain intact for billions of years, creating the stable environment necessary for life to arise, evolve, and thrive. But after a star's explosive death, not all remnants become the ultra-dense neutron stars we've been discussing. For stars like our own sun, the end of life is a far more serene, though no less fascinating, process, leading to the creation of a white dwarf. These Earth-sized embers are the glowing cores left behind after a star sheds its outer layers, and while they may seem like quiet retirees in the cosmic nursing home, some of them hide a shocking magnetic secret. A small but significant percentage of white dwarfs possess magnetic fields of breathtaking strength, measuring in the millions of Gauss. While this is not quite at the universe-bending level of a magnetar, it is still powerful enough to completely dominate the environment of the dead star and create some of the most bizarre visual signatures we can observe from Earth. The formation of these magnetic white dwarfs is a topic of active research, with two leading theories. The first suggests that the intense magnetic field is simply a fossil, a preserved remnant of the field that existed in the star's core during its main sequence life. As the star goes through its giant phase and then blows away its outer envelope, the core collapses down into a white dwarf. If that original core field was strong enough, the collapse would naturally amplify it due to the conservation of magnetic flux, a principle that means as the core gets smaller, its magnetic field gets stronger and more concentrated. The second, more dramatic theory involves a stellar merger. If two white dwarfs in a binary system were to collide and merge, the incredible turbulence and differential rotation during that collision could act as a powerful dynamo, generating a colossal magnetic field in the newly formed single white dwarf. This could explain why some of the most magnetic white dwarfs we find also seem to be more massive than average. The primary way we detect these magnetic powerhouses is through their light, specifically a phenomenon known as Zeeman splitting. Normally, an element like hydrogen in a star's atmosphere will absorb light at very specific, sharp wavelengths, creating dark lines in the star's spectrum that act like a fingerprint, telling us what the star is made of. However, when an atom is placed in an incredibly powerful magnetic field, something strange happens to those electrons. The magnetic field alters the energy levels within the atom, causing each single spectral line to split into 2 or 3 separate components, each polarized in a different direction. To an astronomer on Earth, the spectral line doesn't look like a clean, dark mark anymore. It appears as a broad, blurry, or clearly double-lined feature. The degree of splitting is directly proportional to the strength of the magnetic field, allowing us to measure these immense forces across light years of space with remarkable accuracy. The influence of the field doesn't stop at distorting spectral lines. It fundamentally reshapes the white dwarf's very atmosphere. In a non-magnetic white dwarf, elements settle out under gravity in predictable layers, with heavier elements like oxygen and carbon sinking and lighter hydrogen floating to the top. But a powerful magnetic field can disrupt this simple sedimentation. It can trap ions in its grip, preventing them from sinking and creating a strange, patchy atmosphere where certain elements are concentrated at the magnetic poles. This can lead to wild variations in the observed spectrum as the star rotates, with the chemical composition appearing to change dramatically from our viewpoint. Furthermore, the field is so strong that it can actually suppress convection, the churning motion of gas that normally helps distribute heat. This can result in huge temperature differences between the hotter magnetic poles and the cooler equator, making the surface of a magnetic white dwarf a truly alien and uneven landscape, a far cry from the placid, uniform sphere we might imagine. But for all the incredible magnetic phenomena we've explored, from the perfectly balanced fields of pulsars to the protective duality of Earth's own shield, there is a profound and puzzling asymmetry at the very heart of magnetism itself. Every magnet we have ever found, from the smallest refrigerator magnet to the largest magnetar, has 2 poles, a north and a south. Break a bar magnet in half and you don't get isolated poles, you simply get 2 smaller magnets, each with its own north and south. This duality is a fundamental rule of our universe, so ingrained that we rarely stop to question it. But what if it wasn't always this way? What if there could be a particle with just a single magnetic charge, a north without a south, or a south without a north? This theoretical particle is known as a magnetic monopole, and its potential existence is one of the most tantalizing, missing pieces in all of modern physics. The quest for the magnetic monopole begins with a simple and elegant symmetry in the equations that govern our universe. In the 19th century, James Clerk Maxwell unified the theories of electricity and magnetism into a single set of 4 beautiful equations. These equations work perfectly to describe the world we see, but they contain a noticeable asymmetry. Maxwell's equations show that electric charges, like electrons and protons, exist as isolated units. You can have a positive charge without a negative one nearby. But for magnetism, there is no equivalent source or sink for magnetic field lines. They always form continuous loops. This asymmetry has bothered physicists for over a century. It was the brilliant physicist Paul Dirac who, in 1931, took a deep dive into the quantum mechanics of these equations and made a stunning theoretical discovery. He showed that if just a single magnetic monopole existed somewhere in the universe, it would instantly explain a profound mystery: why electric charge is quantized, meaning why all electric charges in the universe appear to be exact multiples of the charge of an electron. We take this for granted, but there's no fundamental reason why charge has to come in these discrete packets. Dirac found that the existence of a monopole would naturally require electric charge to be quantized, weaving a beautiful and elegant connection between electricity and magnetism that is currently missing from our models. The implications of finding a monopole would extend far beyond just neatening up our equations. It would cause a fundamental rewrite of physics. For one, It would complete the symmetry between electricity and magnetism in a way that is deeply satisfying to physicists. We could then describe all electromagnetic phenomena using sources for both electric and magnetic fields, making the theory even more powerful and universal. But the most revolutionary impact would be on our understanding of the universe's earliest moments. Most grand unified theories, which attempt to merge the electromagnetic, weak, and strong nuclear forces into a single framework, predict that magnetic monopoles must have been created in staggering numbers during the first fractions of a second after the Big Bang. In the unimaginable energy and heat of that primordial instant, the forces of nature were unified into a single superforce. As the universe expanded and cooled, it underwent a series of phase transitions, much like steam condensing into water. It is during these transitions that defects in the fabric of spacetime could have formed, and one type of those topological defects would be a magnetic monopole. If these theories are correct, the early universe should have been flooded with these primordial monopoles. So where are they all? This question is known as the monopole problem, and it was a major motivator for the development of the theory of cosmic inflation. Inflation proposes that the universe underwent a period of exponentially rapid expansion just after the Big Bang. This expansion would have diluted the density of any primordial monopoles to such an extent that they became incredibly rare, effectively solving the problem of why we don't see them everywhere we look. But incredibly rare doesn't mean non-existent, and the hunt for these elusive particles has been going on for decades. Scientists have searched for them in everything from moon rocks and ancient geological samples to the debris from particle accelerator collisions. They've built sophisticated detectors deep underground, shielded from cosmic rays, hoping to catch the unique, immense signature of a monopole's passage. A magnetic monopole would be unlike any other particle. Because it would carry a massive magnetic charge, it would interact very strongly with matter, leaving a clear and unmistakable trail. Despite these extensive searches, no definitive monopole has ever been found, yet the search continues because the prize is so monumental. Discovering a magnetic monopole wouldn't just be about finding a new particle. It would be a direct window into the universe when it was less than a trillionth of a second old, providing incontrovertible evidence for grand unified theories and our concepts of cosmic inflation. It would confirm that the forces we see as separate today were indeed once one, and it would validate some of the most ambitious ideas in theoretical physics. The magnetic monopole remains a ghost in the machine of the cosmos, a theoretical necessity that continues to defy detection, pushing our experiments to their limits and compelling us to look deeper into the foundations of reality. But the influence of magnetism extends far beyond the confines of individual stars or planets, weaving its way through the very fabric of galaxies themselves. We now journey to the largest scale yet, where magnetic fields are not mere features but fundamental architects of cosmic structure. Our own Milky Way and every galaxy like it is permeated by a vast, invisible web of magnetic force. These galactic magnetic fields are astonishingly pervasive, stretching for tens of thousands of light years between the stars, threading through the immense clouds of gas and dust that drift in the interstellar void. Unlike the neatly ordered field of a bar magnet, this is a tangled, complex tapestry, with field lines twisted and folded by the turbulent motions of the galaxy's rotation and the violent lives and deaths of its stars. Detecting something so intangible across such mind-boggling distances is a monumental challenge, but astronomers have a clever toolkit. The primary method relies on a property of light called polarization. As starlight travels through the galaxy, it passes through clouds of interstellar dust. These tiny, elongated dust grains tend to align themselves with the local magnetic field, much like countless microscopic compass needles. When light from a distant star hits these aligned grains, it becomes polarized, meaning its light waves oscillate in a preferred direction perpendicular to the magnetic field. By carefully measuring the polarization of light from thousands of stars across the sky, we can effectively map the direction of the magnetic field lines throughout our galaxy. Another powerful technique uses radio astronomy. Cosmic rays, which are high-energy particles zipping through space, also spiral along galactic magnetic field lines. As they do so, they emit a special kind of radio wave called synchrotron radiation. By mapping this faint radio glow, we can trace out the strength and structure of the magnetic fields that guide these particles, painting a picture of the galaxy's invisible magnetic skeleton. The origin of these immense fields is a cosmic mystery still being unraveled. The leading theory is known as the galactic dynamo. It operates on the same basic principle as the dynamos in planets and stars, but on a vastly grander scale. It starts with a tiny seed magnetic field, which could be primordial, left over from the earliest moments of the universe. As the galaxy rotates, this weak field is stretched and wound up by the differential motion of its spinning disk. The inner parts rotate faster than the outer parts. Simultaneously, turbulence from supernova explosions, stellar winds, and the rise and fall of hot gas provides the chaotic churning motion. This combination of rotation and turbulence amplifies the seed field over hundreds of millions of years, building it up into the powerful, large-scale field we detect today. It's a slow, relentless process that turns the entire galaxy into a magnificent, self-sustaining electromagnetic engine. Once established, these fields play a critical and active role in shaping the galaxy's evolution. One of their most important jobs is governing the birth of new stars. Giant molecular clouds, the stellar nurseries of the galaxy, are supported against their own gravity by a combination of internal gas pressure, turbulence, and magnetic pressure. The magnetic fields within these clouds provide a supporting force that resists gravitational collapse. For a region of the cloud to collapse and form stars, it must somehow shed this magnetic support, likely through a process called ambipolar diffusion, where neutral gas particles slowly drift past the ions that are tied to the magnetic field lines. This means the magnetic field acts as a cosmic regulator, slowing down star formation and preventing all the gas from turning into stars in a single, frantic burst. It ensures that star birth is a gradual, sustained process over billions of years. Furthermore, these galactic fields are the ultimate cosmic ray highways. Cosmic rays, which are mostly protons and atomic nuclei accelerated to near light speed, are believed to originate from the shock waves of supernova remnants. Once created, they don't fly in straight lines. They are trapped by the galaxy's magnetic field. They spiral along the field lines, bouncing back and forth between magnetic irregularities, and are effectively confined to the galaxy for millions of years. This magnetic containment is why we detect a relatively uniform sea of cosmic rays throughout the Milky Way. Without these fields, these high-energy particles would likely escape into intergalactic space almost immediately after their creation. The magnetic web of the galaxy is what corrals them, concentrating their energy and allowing them to influence everything from the chemistry of interstellar gas to potentially even impacting Earth's atmosphere. From guiding the birth of stars to shepherding the most energetic particles in existence, the magnetic fields of galaxies are silent, powerful conductors orchestrating the long-term evolution of these vast island universes. These vast magnetic fields weaving through our galaxy are far more than just a cosmic backdrop. They are the master sculptors of stellar birth, actively participating in the creation of every new star and planet. To witness this process, we must venture into the dark, cold hearts of giant molecular clouds, the majestic stellar nurseries of the cosmos. These clouds are immense, often light years across and containing enough gas and dust to form thousands of stars like our Sun. But they don't collapse into stars easily or quickly. They are held in a delicate balance, and magnetic fields provide one of the most crucial supporting forces against the relentless pull of gravity. Inside these frigid clouds, the gas is partially ionized. This means that while most of the cloud is made up of neutral hydrogen molecules, a small fraction of the atoms have lost an electron, creating positively charged ions and free-floating electrons. These charged particles become intimately tied to the magnetic field lines threading through the cloud. They are effectively frozen into the field and can only move freely along its direction. The magnetic field, therefore, acts as a structured framework permeating the entire cloud. As gravity tries to pull all the material inward to form a star, this magnetic framework resists the collapse, especially in the direction perpendicular to the field lines. It's like trying to compress a bundle of rubber bands. The more you squeeze, the more they push back. This magnetic pressure is a primary reason why these vast clouds can remain stable for millions of years before the slow, majestic process of star formation can begin. For a dense core within one of these clouds to finally collapse and ignite a new star, it must find a way to shed this magnetic support. This happens through a remarkably slow and subtle process called ambipolar diffusion. Remember, the magnetic field lines are locked in place by the charged ions, but the vast majority of the cloud's mass is in the neutral gas. Over immense spans of time, these neutral particles slowly drift and diffuse past the ions that are anchored to the magnetic field. It's a cosmic game of patience where gravity gradually pulls the neutral material inward while the magnetic field, still holding onto the ions, is left behind. This slowly concentrates mass at the cloud's center without the magnetic field's opposing force, until finally gravity wins and the core begins to collapse in earnest. Magnetic fields, in this way, act as the universe's ultimate regulator on star formation, preventing a chaotic and rapid burst of star birth and instead ensuring a slow, sustained, and orderly creation of new suns. Once the collapse is underway, another critical problem emerges: angular momentum. Just as an ice skater spins faster when they pull their arms in, a collapsing cloud of gas will spin more and more rapidly as it shrinks. If this spin weren't somehow slowed down, the material would never be able to fall all the way inward to form a star. It would instead form a vast, spinning disk that would never coalesce. This is where magnetic fields provide another essential service, acting as a cosmic brake system. The young protostar at the center develops a powerful magnetic field of its own. As it rotates, this field sweeps through the surrounding disk of gas and dust like a gigantic, invisible windmill. This interaction transfers angular momentum from the rapidly spinning central star outward to the slower-moving material in the outer disk, effectively slowing the star's spin and allowing material to continue accreting onto it. This process, known as magnetic braking, is vital for allowing the star to grow to its full size. The influence of magnetism doesn't stop with the birth of the star itself. It extends directly to the formation of its entire planetary system. The magnetic field of the young star channels ionized gas from the inner disk along its field lines, causing it to crash down onto the star's surface at the poles in spectacular, high-energy flows called accretion streams. Meanwhile, the magnetic fields within the protoplanetary disk itself play a key role in planet formation. They help stir up turbulence in the disk, which is crucial for allowing dust grains to clump together and eventually form planetesimals, the building blocks of planets. They can also create pressure bumps that trap dust and pebbles, creating dense rings where planets are more likely to form. From governing the initial collapse of a gas cloud to breaking a star's furious spin and shaping the very disk where worlds are born, magnetic fields are the invisible midwives present at the birth of every star and planet in the cosmos. To truly grasp the immense power of a magnetar, we must venture beyond the familiar laws of classical physics and into the bizarre, counterintuitive world of quantum mechanics. This is the realm where the rules change and the influence of a magnetic field becomes even more profound, twisting the very building blocks of matter itself. At this microscopic scale, magnetism isn't just a force that pushes and pulls. It's an intrinsic property woven into the fabric of every electron and proton. This fundamental quality is known as spin. Think of it not as actual physical spinning like a tiny top, but as an innate form of angular momentum, a kind of quantum identity tag that every particle carries. This spin gives each electron its own tiny magnetic moment, effectively making it a minuscule bar magnet. In most materials, these countless tiny magnets point in random directions, canceling each other out. But when an external magnetic field is applied, something extraordinary happens. The field exerts a torque on these electron magnets, forcing them to align with its direction. This alignment is what creates the macroscopic magnetic properties we see in everything from a simple compass needle to a powerful neodymium magnet. Now, imagine applying this principle not to a lump of metal, but to the space inside an atom. In a normal atom, electrons orbit the nucleus in specific energy levels or shells. But place that atom in a magnetic field, and the field interacts with both the orbital motion and the intrinsic spin of every electron. This interaction changes the energy of the electron very slightly, depending on its orientation relative to the field. This is the foundation of the Zeeman effect, a phenomenon we briefly encountered with magnetic white dwarfs. In a weak field, an electron can only occupy certain allowed orientations or quantum states. The magnetic field effectively splits a single energy level into two or more distinct, closely spaced levels. When electrons jump between these split levels, they absorb or emit light at slightly different wavelengths than they normally would. What was once a single, sharp spectral line in a laboratory becomes a trio of lines under the influence of the magnetic field. This Zeeman splitting is a powerful diagnostic tool for astronomers, allowing them to detect and measure magnetic fields in distant stars by analyzing the subtle changes in their starlight. But the environment around a magnetar is not weak. It is the most powerful magnetic field known to exist. Here, the Zeeman effect is not a subtle splitting. It is a catastrophic restructuring of the atom. The field is so overwhelmingly powerful that it dominates the forces that usually govern atomic structure. The magnetic force on an electron can become stronger than the Coulomb force that binds it to its nucleus. In this extreme regime, the electron is no longer confined to a spherical orbital cloud. Instead, the magnetic field compels it to move in a tight, helical path along the field line. The atom is stretched and deformed, transformed from a sphere into a long, thin, cigar-shaped entity. Chemistry, as we know it, simply breaks down. The shapes of atoms and the nature of chemical bonds are entirely dictated by the magnetic field, creating a form of matter that cannot be replicated in any laboratory on Earth. This is matter under the influence of a force so supreme it rewrites the quantum rulebook. This leads us to an even stranger quantum magnetic phenomenon, magnetism that arises without any motion at all. We are accustomed to thinking of magnetism as the result of moving electric charges, like the current in an electromagnet or the orbiting electrons in an atom. However, the intrinsic spin of the electron generates its own magnetism entirely independently. This is the purest form of quantum magnetism. In certain materials, when the temperature is cold enough to minimize random thermal motion, the interaction between these spins can lead to fascinating collective behavior. The spins can spontaneously align over vast distances, creating ferromagnets, the permanent magnets we use every day. Alternatively, they can arrange themselves in alternating patterns, with spins pointing up and down in a regular, repeating order, a state known as antiferromagnetism. While antiferromagnets don't produce an external field, they are crucial in technologies like spintronics and form the basis for understanding more exotic magnetic states. The study of these quantum magnetic interactions is pushing the frontiers of both physics and technology. Researchers are now engineering materials at the atomic level to create novel states of matter, such as spin liquids, where the magnetic spins remain in a fluctuating, entangled soup even at absolute zero, never settling into a fixed order. These exotic states are not just theoretical curiosities. They may hold the key to understanding high-temperature superconductivity and are fundamental to the development of quantum computing, where controlling quantum states is paramount. From the distorted atoms at the surface of a magnetar to the entangled spins in a lab on Earth, the quantum nature of magnetism reveals a layer of reality where the lines between force, matter, and information become beautifully blurred. While we've explored the cosmic scale of magnetism, its influence extends to the most intimate and ancient of partnerships, the vital connection between magnetic fields and life itself. This relationship is not a one-way street where life simply endures a magnetic environment. Many creatures have actively evolved to harness Earth's gentle field, using it as a reliable roadmap for survival. The most iconic example of this is the incredible long-distance navigation of migratory birds. Every year, species like the Arctic tern embark on journeys spanning tens of thousands of kilometers, traveling from pole to pole with astonishing precision. For centuries, how they achieved this feat was one of nature's great mysteries. We now know that they navigate using a sophisticated multi-sensory toolkit that includes visual landmarks, the position of the sun and stars, and even their sense of smell. But their true secret weapon, especially on overcast days or featureless ocean crossings, is a built-in biological compass that senses Earth's magnetic field. This ability, known as magnetoception, isn't exclusive to birds. It's found across the animal kingdom. Sea turtles are born with this sense, using it to embark on their epic transoceanic voyages after hatching on a beach. Salmon use it to find their way back to the precise river of their birth to spawn. Even species of bats, bees, and fish demonstrate a sensitivity to magnetic fields. The mechanism behind this sense is a breathtaking example of nanoscale engineering. Research strongly suggests that many of these animals have tiny, chain-like crystals of an iron oxide mineral called magnetite embedded in their bodies, often in their skulls or beaks. These magnetite crystals are essentially microscopic, permanent magnets. When aligned with Earth's magnetic field, they physically twist and pull on special nerve cells or cellular structures, sending a signal to the brain that provides directional information. It's like having a countless array of minuscule compass needles wired directly into the nervous system, giving the animal a constant, unconscious read on its heading. But the story gets even more fascinating because birds appear to possess a second, entirely separate magnetic sensor that operates on a quantum level. This theory involves a protein in their eyes called cryptochrome. When light, particularly blue light, hits this protein, it initiates a chemical reaction that creates short-lived pairs of molecules called radical pairs. The spin states of these molecules are incredibly sensitive to the direction and strength of the surrounding magnetic field. Depending on the field's orientation, the chemical reaction proceeds slightly differently, potentially creating visual cues that the bird could actually see. In essence, a migratory bird might literally perceive the magnetic field as a subtle pattern of light and shadow overlaid on its vision, a kind of heads-up display guiding it toward its destination. This would mean a bird doesn't just feel north, in a way it might see it. The most ancient masters of this magnetic art, however, are not birds or turtles, but humble bacteria. Certain aquatic bacteria, known as magnetotactic bacteria, take biomagnetism to its logical extreme. Inside their single-celled bodies, they fabricate perfect nano-sized chains of magnetite crystals called magnetosomes. These chains act as a complete and efficient biological compass needle. The bacterium's entire existence is governed by this tool. It uses the chain to passively align itself along Earth's magnetic field lines, which are tilted downward in the northern hemisphere. By simply swimming forward, this alignment helps it quickly find its preferred environment in the water column, moving away from oxygen-rich surface waters and down into the low-oxygen sediments it calls home. They are living proof of a simple, elegant, and ancient navigation system that has been operating for billions of years. a testament to life's incredible ability to adapt and utilize the fundamental forces of its planet. This deep biological connection shows that magnetism is not just an astronomical phenomenon. It is woven into the very fabric of life on Earth, guiding journeys both microscopic and global. While the cosmos demonstrates nature's ultimate magnetic power, humanity has not been idle in its quest to create and control immense magnetic forces here on Earth. Our laboratories have become arenas for engineering magnetic fields of staggering intensity, pushing the very limits of materials science and physics. The pursuit of these powerful fields is driven by a fundamental desire to probe the secrets of matter itself, to see how materials behave under conditions that simply do not occur naturally on our planet. The most powerful steady field magnets we can create, often using superconducting technology, can sustain fields of around 45 Teslas for continuous periods. That's nearly 1,000,000 times stronger than Earth's field, a testament to our engineering prowess. These magnets are workhorses for scientific research, allowing physicists to study the quantum properties of materials, from superconductors to novel two-dimensional substances like graphene in exquisite detail. But to venture into the realm of the truly extreme, scientists must employ a different, more violent strategy: pulsed magnets. These are not instruments of sustained power, but of breathtaking, momentary fury. The principle behind them is a brutal application of raw electrical energy. A massive bank of capacitors, essentially storing a lightning bolt's worth of electricity, is discharged in a fraction of a second through a specially designed coil of wire. The instantaneous current flowing through this coil is so immense, millions of amperes, that it generates a correspondingly immense magnetic field. The forces involved are catastrophic. The magnetic field itself creates a Lorentz force that tries to violently tear the coil apart from the inside. To survive this self-destructive impulse, these magnets are built like fortresses, often reinforced with layers of high-strength materials like carbon fiber or stainless steel, all precisely engineered to hold together for just a few microseconds. The current champions of this explosive technique are the experts at the National High Magnetic Field Laboratory's Pulsed Field Facility, among others around the world. They have succeeded in generating non-destructive pulsed fields exceeding 100 Teslas. To push even further into the multi-hundred Tesla range, scientists sometimes employ a technique called electromagnetic flux compression, or even use high explosives to compress the magnetic field in a controlled implosion. The current world record for a human-made magnetic field stands at an astonishing 1,200 Teslas, achieved in Japan using a method called electromagnetic flux compression, though the coil was destroyed in the process. These fleeting, ultra-high fields open a unique window into the quantum world. When a material is subjected to such an extreme magnetic environment, its electrons are forced into entirely new quantum states. Landau levels, the quantized orbit's electrons are confined to in a magnetic field, become so widely spaced that physicists can observe entirely new electronic and optical phenomena. The applications of this research are profound and far-reaching. By stressing materials to their absolute limits, we can discover new phases of matter, hunt for exotic states like quantum spin liquids, and test the fundamental theories of condensed matter physics under conditions that rival those near a neutron star. This research directly informs the development of new materials with tailored magnetic and electronic properties, which could lead to revolutionary technologies in computing, energy storage, and medicine. Every pulse, every microsecond of magnetic fury is a deliberate step toward understanding the universe's most extreme magnetic environments, right here in a laboratory on Earth. But if we truly want to witness magnetic fields operating at the absolute edge of possibility, we must journey to the most extreme gravitational environment in the universe, the event horizon of a black hole. Here, in the frenzied, final moments before matter vanishes from our reality forever, magnetic fields are not just present, they are the primary architects of some of the most violent and energetic phenomena we can observe. The stage for this drama is the accretion disk, a vast, swirling whirlpool of superheated gas and dust spiraling inward at a significant fraction of the speed of light. As this material is shredded by the black hole's immense tidal forces, it becomes a seething, ionized plasma, a perfect conductor for generating and sustaining immense magnetic fields. The incredible shear forces within the disk, where inner regions orbit much faster than outer ones, twist and stretch these magnetic field lines like strands of cosmic taffy, wrapping them around the black hole and amplifying them to extraordinary strength. These wound-up magnetic fields become the central engine for one of the black hole's most spectacular features, its relativistic jets. These are narrow, focused beams of matter and energy that erupt from the poles of the black hole at nearly the speed of light, often extending for thousands or even millions of light years into intergalactic space. The process that creates them is a masterpiece of magnetic engineering. As the black hole and its inner accretion disk rotate, they drag these immensely powerful magnetic field lines around with them. This creates a coiled, spring-like structure that acts as a natural particle accelerator. Charged particles within the disk get caught in this magnetic grip and are funneled along the field lines away from the disk's plane and toward the poles. The magnetic field doesn't just guide them, it accelerates them with unimaginable force, pumping energy into them until they are screaming outward at relativistic velocities. This is how a black hole, an object known for pulling everything in, paradoxically becomes the most efficient particle cannon in the cosmos, shooting out material that would otherwise be lost forever. The influence of these magnetic fields extends all the way down to the black hole's point of no return. While gravity is the dominant force pulling material inward, magnetism provides a crucial counterbalance that dictates how and when matter finally crosses the event horizon. The magnetic fields embedded in the accretion disk create a powerful pressure that can actually support the gas against gravity's relentless pull, slowing its inward spiral and regulating the feeding rate of the black hole. In some regions, magnetic forces can even halt the flow entirely, creating a traffic jam of hot plasma that glows brilliantly before finally overcoming the magnetic barrier. Furthermore, the process of magnetic reconnection, which we discussed with solar flares, occurs here on a vastly more energetic scale. When these highly stressed magnetic field lines suddenly snap and reconnect near the inner edge of the disk, they release colossal bursts of energy that can heat the surrounding plasma to temperatures of billions of degrees and produce intense flares of X-ray and gamma-ray radiation that we can detect across the universe. The chaotic dance between gravity's inexorable pull and magnetism's structured resistance is what makes the region around a black hole such a turbulent and luminous environment, proving that even the universe's ultimate vacuum cleaners are governed by the invisible hand of magnetic force. While the magnetic field surrounding our planet is a steadfast guardian, it is not an unchanging constant. In fact, one of the most astonishing facts about Earth's magnetism is that it is fundamentally unstable over long periods of time. Our compasses point north today, but there is overwhelming geological evidence that throughout Earth's history, the magnetic poles have repeatedly swapped places. The North Magnetic Pole has become the South, and the South has become the North, in a grand planetary flip-flop that occurs at seemingly random intervals. This process of magnetic reversal is not a rapid, catastrophic event, but a long, drawn-out transformation where the field first weakens, becomes complex and messy, and then gradually re-establishes itself with the opposite polarity. The primary evidence for these reversals is locked within the very rock of the ocean floor. As volcanic magma erupts from mid-ocean ridges and cools to form new crust, tiny magnetic minerals within the rock, like magnetite, act like countless miniature compass needles. As the rock solidifies, these minerals align themselves with the direction and polarity of Earth's magnetic field at that exact moment in time, freezing that magnetic signature into the rock forever. This creates a permanent recording of the planet's magnetic history. As new crust is continuously formed at these ridges, it pushes the older crust outward, creating a symmetrical striped pattern on either side of the ridge. Scientists mapping these stripes with magnetometers have discovered that they are not uniform. They are a series of alternating bands, one band with minerals aligned to today's magnetic north and the adjacent band aligned to the south. This zebra stripe pattern across the world's oceans is the definitive proof that our planet's magnetic field has reversed itself hundreds of times throughout its history. The timing of these reversals is entirely irregular, almost chaotic. There is no reliable cycle or schedule. Some periods, known as supercrons, have seen the field maintain a stable polarity for tens of millions of years. At other times, reversals have happened as frequently as every few 100,000 years. On average, over the last 20 million years, a reversal has occurred about every 200 to 300,000 years. The last full reversal, known as the Bruns-Matayama reversal, happened approximately 780,000 years ago. This means that, statistically speaking, we are long overdue for another flip, though the irregular nature of the process makes any prediction impossible. What exactly happens during a reversal is a subject of intense study. It is not a simple, clean swap. As the dynamo deep in Earth's core becomes turbulent, the main dipole field, the simple north-south bar magnet structure, begins to weaken significantly, perhaps to as little as 10% of its normal strength. During this weakened phase, which can last for a few thousand years, the field doesn't vanish entirely. Instead, it becomes much more complex. Multiple magnetic poles can pop up in strange places around the globe. You might have a North Pole in South Africa and another in the Arctic, creating a chaotic and unpredictable magnetic landscape. This period of a weak, multipolar field would have significant consequences for life on Earth. Our protective shield against solar and cosmic radiation would be severely compromised. With a weakened magnetosphere, more high-energy particles would reach the upper atmosphere, potentially increasing the rate of mutations in DNA and raising the background radiation levels at the surface. It could also lead to more spectacular and widespread auroras, visible at much lower latitudes than normal, as charged particles penetrate deeper into the atmosphere. The good news is that there is no evidence in the fossil record linking past mass extinctions to magnetic reversals. Life has persisted through hundreds of these flips. The main impact on our modern world would be technological, not existential. Our reliance on satellites would face a serious challenge. With a weakened magnetosphere, orbiting satellites would be exposed to much higher levels of radiation, leading to more frequent glitches, system failures, and a shortened operational lifespan. This would affect everything from GPS and telecommunications to weather forecasting and military operations. Furthermore, the complex, shifting field during the transition would render magnetic compasses utterly useless for navigation, forcing us to rely entirely on satellite-based systems at the very time they are most vulnerable. The process of a magnetic reversal is a profound reminder that our planet is a dynamic, living system, with a molten heart that is constantly churning and reshaping the invisible forces that both protect us and guide our way. But our exploration of cosmic magnetism isn't confined to our own solar neighborhood. As we discover thousands of worlds orbiting distant stars, a profound new question emerges. Do these alien worlds also possess their own magnetic shields? The search for magnetic fields on exoplanets is one of the most challenging and exciting frontiers in modern astronomy, pushing our technology to its absolute limits. We cannot yet directly image the magnetic bubble of an exoplanet. Instead, astronomers must become cosmic detectives looking for subtle, indirect clues. One of the most promising methods involves watching for the interaction between an exoplanet and its host star. Just as the solar wind slams into Earth's magnetosphere, creating a bow shock and a long magnetotail, a planet orbiting close to an active star will have its magnetic field buffeted by the stellar wind. If the planet has a strong magnetic field, this interaction can be intense enough to cause the planet itself to emit radio waves, particularly at low frequencies. While we haven't definitively detected this yet with current telescopes, next-generation instruments are being designed specifically to listen for this faint, telltale radio whisper from distant worlds. Another ingenious technique looks for the protection a magnetic field provides. When a planet passes in front of its star from our viewpoint, an event called a transit, it causes a tiny, periodic dip in the star's brightness. By studying the light that filters through the planet's atmosphere during these transits, we can determine its composition. For some exoplanets, particularly those orbiting close to their stars, astronomers have observed that they appear to be losing their atmospheres, with tails of hydrogen and other gases being stripped away by the intense stellar radiation. However, some planets in similar hostile environments show much less atmospheric loss. The leading hypothesis is that these resilient worlds are likely protected by a global magnetic field, which deflects the stellar wind and dramatically slows the erosion of their life-sustaining air. In this way, the absence of a signal, the preservation of an atmosphere, becomes a powerful indirect evidence for the presence of a magnetic shield. The potential implications for life are enormous. Here on Earth, we take our magnetic field for granted, but it is a silent guardian. It fends off the solar wind, preventing our atmosphere from being slowly stripped away into the void of space over billions of years. Without it, our planet might have ended up like Mars, a cold, dry desert with only a wisp of an atmosphere left. For an exoplanet to be a true candidate for harboring life as we know it, it likely needs to be more than just the right distance from its star to have liquid water. It may also need this invisible force field. A strong magnetosphere would protect any potential life on the surface from being bombarded by lethal doses of high-energy particles from its star, which could otherwise sterilize the planet. It safeguards the atmosphere, which regulates temperature and provides the essential chemicals for biology. So, when we scan the heavens for signs of other living worlds, we are not just looking for water or oxygen. We are, in a very real sense, also searching for the magnetic signature of a protected home. The detection of an exoplanetary magnetic field would be a monumental step forward, transforming a distant dot of light from a mere planet into a world that has the fundamental right conditions to be alive. These high-energy particles screaming across the galaxy don't just fly in straight lines. They are guided, contained, and accelerated by the very magnetic web we just explored. The journey of a single cosmic ray proton is a tumultuous million-year odyssey, a pinball game on a galactic scale where the bumpers and flippers are made of invisible magnetic force. Born from the shock waves of supernova explosions, these particles are injected into the interstellar medium with tremendous energy, but they don't simply escape into the void. Instead, they become trapped by the galaxy's magnetic field, spiraling around its lines at nearly the speed of light. This spiraling motion is the key to their long confinement. A proton might travel along a field line for a light year, only to be scattered by a turbulent kink in the field, bouncing back the way it came or being shunted onto a new magnetic pathway. This constant scattering and redirection means a cosmic ray does not take a direct route. It performs a random walk, a drunken stumble through the galaxy's magnetic maze, which can keep it within the Milky Way's disk for millions of years before it finally finds an exit or loses its energy. This magnetic containment does more than just trap the particles. It acts as a natural and incredibly efficient particle accelerator. The original supernova blast provides the initial kick, but the magnetic fields provide the sustained boost. As a cosmic ray travels through a region where the magnetic field is moving, such as a propagating shock wave from a stellar explosion, it can gain energy with each crossing. It's akin to a surfer catching a wave being pushed forward repeatedly by the wave's motion. This process, known as diffusive shock acceleration or Fermi acceleration, can repeatedly slam a proton with magnetic force, boosting its energy to levels far beyond what any human-built accelerator like the Large Hadron Collider could ever achieve. These particles become the most energetic things in the galaxy, all thanks to the magnetic fields that shepherd them. When these ultra-high-energy particles finally do approach our solar system, they encounter a new set of magnetic rules, those of our Sun. The solar wind, blowing outward in all directions, carries with it the Sun's own magnetic field, stretched into a spiral pattern by the Sun's rotation. This creates a vast bubble called the heliosphere, within which the magnetic influence of our star dominates. For a cosmic ray coming from interstellar space, entering the heliosphere is like trying to swim upstream against a powerful, magnetized current. The solar wind and its embedded magnetic field act as a protective buffer, deflecting lower-energy cosmic rays and modulating the number that can actually reach the inner solar system. This modulation isn't constant. It ebbs and flows with the 11-year solar activity cycle. When the Sun is at its most active, with more sunspots and a stronger, more turbulent solar wind, it does a better job of shielding us, and the flux of cosmic rays reaching Earth actually decreases. When the Sun is quiet, the shield weakens and more of these galactic particles can make it through. This constant rain of high-energy particles, guided across light years by magnetic fields, has a direct and tangible effect on our planet. When these primary cosmic rays, mostly protons, collide with atoms in the upper atmosphere, they create a spectacular secondary shower of particles. This air shower can include everything from muons and pions to electrons and gamma rays cascading down toward the surface. While this sounds alarming, our thick atmosphere protects us from the worst of it, absorbing the energy and preventing harmful levels of radiation from reaching the ground. However, this natural phenomenon is not without its impacts. These atmospheric collisions are responsible for creating a portion of the radioactive carbon-14 isotopes that we use for carbon dating ancient organic materials. The cosmic rays are quite literally writing a faint radioactive signature into the history of life on Earth. Furthermore, this particle rain can influence cloud formation and potentially even affect electrical circuits in the atmosphere, contributing to the never-ending and complex conversation between our planet and the galaxy beyond. The journey of a cosmic ray, from its violent birth in a dying star to its final collision in our sky, is a powerful testament to the galaxy's magnetic fields acting as the ultimate conductors of a high-energy symphony. Moving from the turbulent hearts of black holes and the grand scales of galaxies, we find that magnetic fields are also the universe's most masterful artists, sculpting the raw material of space into some of the most breathtaking structures we have ever witnessed, the magnificent nebulae. These vast clouds of gas and dust are far more than just pretty cosmic scenery. They are dynamic workshops where stars are born and die, and their stunning forms. The delicate pillars, the graceful loops, the intricate filaments are largely shaped by the invisible hand of magnetism. When we look at a Hubble image of the iconic pillars of creation in the Eagle Nebula, we are not just seeing a passive cloud. We are witnessing a colossal sculpture in progress, with magnetic fields acting as the primary chisel. The process begins with the same partially ionized gas we find in molecular clouds. Within a nebula, ultraviolet radiation from nearby hot, young stars strips electrons from atoms, creating a plasma of ions and free electrons. These charged particles become ensnared by any ambient magnetic field that permeates the cloud. Once trapped, they can only flow easily along the direction of the magnetic field lines, while their motion across the lines is heavily restricted. This means the magnetic field imposes a kind of order on the chaos, creating a preferred direction for the structure of the nebula. As gravity, radiation pressure, and stellar winds from new stars buffet the cloud, trying to push it into a spherical shape, The magnetic field provides a supporting skeleton that resists this pressure in certain directions, forcing the gas and dust to collapse and flow primarily along the magnetic field lines. The result isn't a formless blob, but an elongated structure, a filament, or a sheet. This is why so many nebulae exhibit such striking filamentary structures. Instead of dispersing evenly, the dust and gas are channeled, gathered into vast, river-like ribbons that can stretch for light years. The famous Veil Nebula, the expanding remnant of a supernova explosion, is a perfect example. Its delicate, lace-like filaments are not random shreds of debris. They are precisely where the shock wave from the ancient explosion collided with and compressed the pre-existing galactic magnetic field. The ionized gas became trapped along these lines, glowing to reveal the intricate magnetic web that was always there, hidden in the void. In star-forming regions like the Orion Nebula, we see a similar phenomenon. The magnetic field guides the flow of material, creating the towering pillars that are actually denser knots of gas and dust shielding themselves from the intense stellar radiation, while the surrounding less dense material is eroded away. The influence of magnetism extends to the very smallest scales within these clouds, governing the alignment of interstellar dust grains. These tiny particles, many no larger than a fraction of a micrometer across, are not spherical. They are elongated, almost like miniature grains of rice. As they drift through the magnetized nebula, they experience a torque that causes them to spin and align their longest axis perpendicular to the direction of the local magnetic field. This might seem like a minuscule detail, but it has a profound effect on how we see the universe. This ordered alignment causes a phenomenon called interstellar polarization. The light from stars behind the nebula, as it passes through this veil of aligned dust grains, becomes polarized. The dust preferentially scatters and absorbs light vibrating in one direction, meaning the light that emerges is oriented in a specific way. Astronomers use specialized cameras to detect this polarization, and in doing so, they can effectively map the magnetic field lines throughout the nebula without directly seeing them. The result is often a stunning image overlay showing a gentle, flowing pattern of lines tracing the contours of the gas clouds, revealing the invisible architecture that holds the entire structure together. This magnetic framework does more than just create beauty. It regulates the birth of new stars within these nurseries. By providing support against gravity, it slows down the collapse of gas, preventing the entire nebula from turning into stars in a single, frantic burst. It ensures that star formation is a gradual, sustained process, allowing solar systems like our own the time to form peacefully within the magnetic embrace of their natal cloud. So the next time you gaze upon an image of a glowing nebula, remember you are not just looking at a cloud of gas, you are seeing a magnificent magnetic sculpture, a masterpiece of force and form written across the canvas of space. Detecting these colossal yet invisible cosmic forces requires astronomers to become master detectives, employing a sophisticated toolkit of indirect methods to read the faint signatures that magnetic fields leave on the light that travels across the universe. The first and most direct technique relies on a fundamental quantum effect we've touched on before, the Zeeman effect. This method acts like a cosmic strain gauge for magnetism. When an atom is placed in a magnetic field, the energy levels of its electrons are slightly altered, causing the spectral lines it produces to split into 2 or 3 closely spaced components. The wider this splitting, the stronger the magnetic field. By analyzing the light from a distant star with a powerful spectrograph, astronomers can measure this subtle splitting of spectral lines like hydrogen or iron and calculate the field strength with remarkable precision. This is how we first confirmed the monstrous fields of magnetic white dwarfs and how we continue to measure the surface fields of stars throughout our galaxy. It's a brilliant piece of cosmic forensics, turning a star's light into a direct magnetic field report. But the Zeeman effect has its limits, especially when trying to probe the vast, diffuse magnetic fields that fill the space between the stars. For mapping these galactic scale fields, astronomers turn to a different clue: the polarization of light. This technique relies on the humble interstellar dust grain. These tiny, elongated particles tend to align themselves perpendicular to the local magnetic field, much like countless microscopic compass needles. When starlight travels through a cloud of this magnetically aligned dust, the dust grains preferentially absorb and scatter light vibrating in one particular direction. This process polarizes the light, meaning the light waves end up oscillating in a preferred plane. By meticulously measuring the polarization of light from thousands of background stars, astronomers can essentially trace the orientation of the magnetic field lines threading the entire dust cloud. It's like seeing the invisible magnetic landscape revealed by the shadow it casts on starlight. For the most energetic magnetic environments, there's a third, even more dramatic signature: synchrotron radiation. This is the brilliant, non-thermal glow created when ultra-relativistic electrons, those moving at a significant fraction of the speed of light, spiral along magnetic field lines. The process is a fantastic natural particle accelerator at work. As each electron is forced into a curved path by the magnetic field, it loses energy by emitting radiation across a broad spectrum, often brightest in radio waves. This light is highly polarized and has a very distinctive spectrum, instantly betraying the presence of both high-energy electrons and a magnetic field. We see this unmistakable signature everywhere we find powerful magnetic fields and energetic particles, billowing from the remnants of supernova explosions, jetting from active galactic nuclei, and creating a faint radio haze throughout our own galaxy's disk. Mapping synchrotron radiation allows us to trace the strength and structure of magnetic fields in the most violent and dynamic corners of the cosmos. Combining these techniques creates a powerful multi-wavelength approach to cosmic magnetic forensics. Radio telescopes chart the grand architecture of galactic fields through synchrotron maps. Optical and infrared telescopes reveal the finer details within nebulae and star-forming regions through polarization studies, and spectroscopic observations provide the hard numbers on field strength for individual objects via the Zeeman effect. Together, they allow us to piece together a comprehensive map of the universe's invisible magnetic skeleton, proving that even though we cannot see these forces directly, their imprint on light itself provides all the evidence we need to understand their immense power and pervasive influence. Yet the story of cosmic magnetism doesn't begin with swirling galaxies or dying stars. Its origins stretch all the way back to the very birth of the universe itself. To understand where these immense forces came from, we must rewind the cosmic clock to the first fraction of a second after the Big Bang, a period of unimaginable energy and rapid expansion when the very laws of physics were still settling into place. The question of how magnetic fields originated in this primordial soup is one of the most profound puzzles in cosmology. Were they present at the very beginning, woven into the fabric of spacetime itself, or were they forged in the fires of the universe's infancy, emerging from the chaotic processes that shaped everything we see today? One leading theory takes us to a pivotal moment called the electroweak phase transition. In the universe's first trillionth of a second, the fundamental forces we know today, electromagnetism and the weak nuclear force, were unified into a single, symmetric force. As the universe expanded and cooled, it underwent a cosmic phase change, much like steam condensing into water. During this transition, the symmetry between these forces was broken, giving rise to the distinct electromagnetic and weak forces we observe now. It's theorized that this sudden shift in the state of the universe could have created tiny imperfections or defects in the fabric of spacetime. These defects, much like cracks forming in ice as it freezes, could have generated incredibly weak primordial magnetic fields. These fields would have been minuscule, perhaps spanning only subatomic scales initially, but they were the first seeds of magnetism in the cosmos. Another compelling hypothesis points to the inflationary epoch, a period of exponentially rapid expansion thought to have occurred even earlier. Inflation would have stretched quantum fluctuations, tiny, random variations in energy and density that exist even in a vacuum, to macroscopic scales. Some physicists propose that among these amplified fluctuations could have been the precursors to magnetic fields. In this scenario, the violent stretching of spacetime itself could have generated these first magnetic seeds. Regardless of their exact origin, these initial fields would have been incredibly weak and chaotic, a faint magnetic whisper across the newborn universe. But they were crucially important. They provided the raw material that later cosmic processes would amplify into the powerful fields we see today. The real work of building the magnetic universe began after this initial seeding. For hundreds of millions of years, these weak primordial fields were present, but they permeated a universe that was dark, neutral, and largely devoid of the structure needed to amplify them. This all changed with the formation of the first stars and galaxies. As matter collapsed under gravity to form these first structures, it did so in a universe already threaded with these faint magnetic threads. The process of structure formation itself acted as a first amplifier. As gas flowed along the filaments of the cosmic web into the gravitational wells of dark matter, it compressed the magnetic field lines frozen within it, gently strengthening them. This is similar to what happens when an ice skater pulls their arms in to spin faster. As the gas collapses, the magnetic field is concentrated and intensified. Then, with the dawn of the first stars and galaxies, the true engines of magnetic amplification, dynamos, kicked into gear. The same basic process that operates in Earth's core and in stars began to work on a galactic scale. The rotation of these nascent galaxies, combined with turbulent motions from supernova explosions, stellar winds, and the accretion of new material, began to stretch, twist, and fold these weak seed fields. This chaotic motion, acting over hundreds of millions of years, could amplify a weak primordial field by a factor of 1 trillion or more, transforming it into the coherent micro-Gauss strength fields we observe threading galaxies today. This galactic dynamo effect is thought to be the primary mechanism for building the large-scale magnetic structures we see, effectively taking the universe's faint magnetic whisper and turning it into a powerful, sustained hum. The evolution of cosmic magnetic fields is therefore a grand story of transformation, from quantum seeds to galactic-scale power. These fields have not been passive passengers in the universe's expansion. They have played an active and dynamic role in shaping cosmic evolution. They influenced the collapse of the first gas clouds, regulated the birth of stars in early galaxies, and provided the pathways for the first cosmic rays to travel. Understanding their origin is not just about tracing the history of magnetism. It's about completing our picture of how the universe grew from a smooth, hot plasma into the complex, structured, and magnetically rich cosmos we observe today. The faint echoes of those first magnetic moments are still with us, woven into the fabric of every galaxy and illuminated in the glow of every nebula, a permanent reminder of forces born in the universe's first breath. But to truly appreciate the universe's most extreme magnetic environments, we must venture beyond even the quantum realm and into the mind-bending domain of Einstein's theory of general relativity, where gravity warps the very fabric of spacetime itself. It is here, in the crushing grip of a neutron star or a black hole, that magnetic fields reveal another astonishing power, the ability to influence the very passage of time. We often think of time as a constant, universal tick of a clock, but Einstein revealed that it is malleable, flowing at different rates depending on gravity and velocity. A strong gravitational field, like that at the surface of a neutron star, slows time down relative to a distant observer. This is the well-known effect of gravitational time dilation. However, an immensely powerful magnetic field introduces a fascinating and often overlooked relativistic twist to this phenomenon. The key lies in understanding that, according to Einstein, energy and mass are two sides of the same coin, perfectly equivalent as described by his famous equation. A magnetic field, though invisible, is not nothing. It contains an enormous density of energy. In the vicinity of a magnetar, where the magnetic energy is almost unimaginably concentrated, this energy density becomes so extreme that it itself contributes to the warping of spacetime. It effectively adds to the gravitational curvature caused by the star's mass. This means the spacetime around a highly magnetized neutron star is not just warped by its gravity, but also by the sheer energy stored in its magnetic field. For a hypothetical observer daring enough to orbit near a magnetar, clocks would tick noticeably slower due to the combined effects of the intense gravity and the powerful magnetic field, a phenomenon we could call magneto-temporal distortion. This warping of spacetime by magnetic energy has a direct and bizarre consequence for light itself, an effect known as vacuum birefringence. In the empty vacuum of space, light normally travels in a straight line, with its electric and magnetic components vibrating in all directions perpendicular to its path. However, in the presence of an ultra-strong magnetic field, the nature of the vacuum itself is altered. Quantum electrodynamics tells us that a vacuum is not completely empty. It is seething with virtual particle-antiparticle pairs constantly flashing in and out of existence. An extreme magnetic field polarizes this quantum vacuum, influencing these virtual particles and effectively making space itself behave like a crystal. This means that light traveling through this magnetized vacuum will have its propagation speed slightly altered depending on its polarization direction. Light vibrating parallel to the magnetic field will travel at a different speed than light vibrating perpendicular to it. This bizarre splitting of light was predicted decades ago, but was thought to only be observable near the most magnetic objects in the universe. In a monumental discovery, astronomers studying the neutron star candidate 1E 1207 5209 with the European Southern Observatory's Very Large Telescope confirmed the effect for the first time. They detected a degree of linear polarization in the star's light that could only be explained by vacuum birefringence occurring in the incredible magnetic field just above its surface. This was a direct observational validation of a quantum effect predicted by Einstein's theory, made possible by the existence of these cosmic magnetic monsters. It proves that in these extreme environments, magnetism doesn't just bend the path of light. It changes the fundamental optical properties of nothingness itself. The interplay between magnetism and relativity becomes even more dramatic near a black hole. Here, the magnetic fields trapped in the frenzied accretion disk are not just spectators to the gravitational madness, they are active participants. As we've discussed, these wound-up fields power the relativistic jets, but they also influence how we perceive time and events near the event horizon. The incredible energy density of the magnetic field adds to the stress-energy tensor that tells spacetime how to curve, subtly altering the geometry around the black hole. Furthermore, for matter spiraling inward, the magnetic forces can impart tremendous acceleration, adding velocity-based time dilation to the already significant gravitational time dilation. An atom caught in the magnetic grip of the inner accretion disk might experience seconds while millennia pass in the external universe, a prisoner of both gravity and magnetism's relentless grip. This confluence of forces creates a laboratory for physics under conditions we can never hope to replicate on Earth, where the universe's most powerful magnets illuminate the deepest secrets of relativity. Moving from the colossal remnants of dead stars, we find that powerful magnetism is not exclusive to stellar success stories. In the cosmic hierarchy, there exists a curious class of objects that occupy a mysterious middle ground, too massive to be called planets yet too small to ignite as true stars. These are brown dwarfs, often dubbed failed stars, and they hold a surprising magnetic secret all their own. A brown dwarf forms much like a star from the collapse of a cloud of gas and dust, but it simply never gathers enough mass, typically between 13 and 80 times the mass of Jupiter, to trigger the sustained fusion of hydrogen in its core. Without this central engine, it cannot blaze with the fiery light of a true star. Instead, it slowly cools and fades over billions of years, a dim, ember-like object lingering in the dark. Yet, despite this failed stellar ambition, brown dwarfs are anything but magnetically quiet. These substellar objects generate and sustain magnetic fields that are remarkably powerful, often thousands of times stronger than Jupiter's immense field and rivaling those found in the most active low-mass stars. This presents a fascinating puzzle for astronomers. A star like our Sun generates its magnetic field through that churning dynamo in its convective zone, where moving plasma acts like an electrical conductor. A gas giant planet like Jupiter generates its field through the convection of metallic hydrogen deep in its pressurized interior, but a brown dwarf exists in a strange limbo. It is too hot and low pressure to have a layer of metallic hydrogen like Jupiter, yet without full-fledged fusion, its internal structure and energy flow are different from a star's. So how does it create such a strong magnetic field? The leading theory suggests that brown dwarfs operate with a dynamo that is a unique hybrid of both planetary and stellar mechanisms. Their interiors are believed to be fully convective. There are no STABLE Chinese letter like there are in parts of the Sun. This means the entire interior of the brown dwarf is in a state of constant turbulent motion, much like a pot of vigorously boiling water. This churning plasma, which is hot and ionized enough to be an excellent electrical conductor, coupled with the brown dwarf's rapid rotation, many spin so fast they complete a full rotation in just a few hours, creates the perfect conditions for a dynamo effect. It's this combination of total convection and fast spin that amplifies and sustains magnetic fields of shocking strength, proving that you don't need a star's nuclear heart to be a magnetic powerhouse. The effects of this hidden magnetic power are not theoretical. We can actually observe them from Earth. The most dramatic evidence comes in the form of spectacular auroras, but these are not like the delicate polar lights we see on our own planet. The auroras on brown dwarfs are planet-sized tempests of light, raging across their entire atmospheres and shining millions of times brighter than any aurora in our solar system. However, there's a crucial difference in what causes them. On Earth, auroras are driven by particles from the solar wind channeled by our magnetic field. A lonely brown dwarf with no nearby star to provide a solar wind must have a different particle source. Scientists believe these immense light shows are likely powered by a process similar to what happens on Jupiter, where particles are pumped into the magnetic environment by a volcanic moon. But without a moon like Io, the brown dwarf might be drawing material from a nearby planetary companion or even accelerating particles from its own upper atmosphere, creating a self-generating auroral engine that lights up the void around it. These auroras are not just invisible light, they are accompanied by intense, beamed radio emissions. In fact, the way we often first detect the magnetic activity of a brown dwarf is by listening to the cosmos with radio telescopes. As electrons spiral along the brown dwarf's powerful magnetic field lines, they generate cyclotron maser emissions, a highly directed, lighthouse-like beam of radio waves that sweeps through space with each rotation of the object. This powerful, periodic radio pulse is a dead giveaway of a strong magnetic field and a rapidly spinning object. By studying the timing and polarization of these radio signals, astronomers can not only confirm the field's existence but also map its strength and structure, uncovering the secrets of a dynamo process working in nature's most enigmatic objects. These failed stars, glowing faintly with infrared heat and crackling with magnetic energy, remind us that the universe's magnetic creativity extends far beyond the simple categories of planets and stars, flourishing even in the realms of cosmic ambiguity. But to truly understand the forces at work in magnetars and supernova, we cannot simply wait for cosmic events to unfold light years away. We must bring a piece of that extreme physics right into our laboratories. This is the thrilling frontier of laboratory astrophysics, where scientists use some of the most powerful tools on Earth to recreate the magnetic fury of the cosmos on a tabletop. The primary challenge is generating a magnetic field that is not only incredibly strong, but also exists within a seething, ionized gas, a plasma, mimicking the conditions found in stellar interiors and supernova remnants. To achieve this, researchers employ a two-pronged approach, using both massive, sustained magnets and brief, explosive bursts of energy from high-power lasers. The first method involves using sophisticated pulsed magnets, like those we discussed earlier, to generate fields of 100 Teslas or more. While these are incredible for studying condensed matter, to truly simulate an astrophysical plasma, scientists combine these magnets with devices that can generate the hot, dense plasma itself. One such tool is the Z-pinch machine. Here, a massive electrical current is driven through a thin cylinder of metallic wires or a gas puff. The current creates its own magnetic field, which then pinches the plasma inward, compressing it and heating it to temperatures of millions of degrees while simultaneously amplifying the magnetic field to extreme levels through the compression. This setup can create conditions eerily similar to those in the outer atmospheres of stars or in the shocked material of a supernova blast wave, allowing researchers to watch how plasma and magnetic fields interact under stellar pressures. The second, and even more dramatic, approach involves the world's most powerful lasers, like the National Ignition Facility in the United States or the Laser Megajoule in France. In these experiments, researchers don't try to generate the magnetic field first. Instead, they use the laser to create the astrophysical condition, and the magnetic field naturally emerges from the chaos. They focus the intense beam of a petawatt-class laser onto a tiny target, often a fine wire or a small dot of material. The laser's energy is delivered in an impossibly short pulse, a fraction of a billionth of a second, but within that instant, it deposits more power than the entire electrical grid of a large nation. This instantly vaporizes the target, turning it into a rapidly expanding plasma fireball. This explosion is so violent and asymmetric that it creates incredibly powerful shock waves and streams of electrons moving at different velocities within the plasma. And as we know, whenever charged particles move in different ways, magnetic fields are born. This process, known as a Biermann battery, effectively uses the chaotic energy of the laser-driven explosion to generate magnetic fields that can reach thousands of Teslas, albeit for a fleeting nanosecond. While this field exists for a literal blink of an eye, that is often long enough for the intricate diagnostics surrounding the experiment to capture its effect on the plasma. By studying how these self-generated fields grow, how they twist and channel the plasma, and how they might dissipate energy, physicists can test their models of how magnetic fields are born in the first moments after a supernova or within the accretion disks around young stars. The real power of these experiments is visualization. In space, we see the aftermath of magnetic processes, the shaped nebulae, the glowing remnants. But in the lab, with incredibly fast cameras and X-ray diagnostics, researchers can actually watch the process unfold in ultra-slow motion. They can see the plasma being churned by turbulence, observe the magnetic field lines being stretched and folded by that turbulence in a process that amplifies the field, and witness the stunning phenomenon of magnetic reconnection as those field lines snap and reorder themselves, releasing their stored energy in a micro-burst that mimics a solar flare. This allows them to test and refine the computer simulations used to model astrophysical events, moving from educated guesses to experimentally verified physics. These laboratory creations will never match the sheer scale or duration of a cosmic magnetic field, but they provide a priceless, controlled window into the fundamental physics that governs some of the most energetic and magnetic events in the history of our universe. Now we venture into one of the most profound and speculative mysteries of modern cosmology: the potential and utterly enigmatic connection between the magnetic fields we can observe and the dark matter we cannot. For all their power, the magnetic fields we've explored are still a phenomenon of the visible universe, made of the ordinary protons, neutrons, and electrons that constitute stars, planets, and us. But what about the invisible 85% of the matter in the universe, the dark matter that reveals itself only through its gravitational pull? Could this mysterious substance, which refuses to interact with light or magnetic fields in any way we've yet detected, somehow be involved in the cosmic magnetic story? Theorists are beginning to explore this tantalizing frontier, and the possibilities are as fascinating as they are elusive. The standard model of cosmology, known as lambda CDM, describes dark matter as cold and collisionless. This means it moves slowly compared to the speed of light, and its particles interact with each other and with normal matter overwhelmingly through gravity alone. They are not expected to have an electric charge or a magnetic moment. If they did, we likely would have detected their influence by now. This has traditionally painted a picture of dark matter as a silent, passive ghost, simply providing the gravitational scaffolding upon which the visible universe builds its galaxies, while remaining utterly aloof from the electromagnetic drama playing out within them. However, as our observations become more precise, some are asking if this picture is a little too simple. Could there be a subtler, more complex relationship? One intriguing line of speculation suggests that dark matter might not just be a spectator, but could actually be a source of magnetic fields itself. This would require at least a small fraction of dark matter particles to possess a tiny property known as a dark magnetic moment. This wouldn't be magnetism as we know it from electromagnetism, but an analogous force within the hidden, dark sector of physics. If such particles existed, their collective motion and interactions within dark matter halos could potentially generate large-scale, dark magnetic fields. These fields would be completely invisible to us as they wouldn't interact with normal matter. However, they could play a crucial role in shaping the dark matter itself, perhaps helping to solve small-scale problems in our simulations, like why dark matter halos appear less dense in their centers than our models predict. These dark fields could provide a form of pressure that prevents overconcentration. The real magic and the potential for a detectable signature arises if there is a portal, a theoretical, feeble interaction between this dark sector and our own. Through this portal, a dark magnetic field could potentially induce a very weak magnetic field in the normal world. Imagine the dark matter halo of our galaxy, not just as a massive, invisible cloud, but as a generator for a faint, pervasive background magnetic field that we've simply attributed to other sources. Alternatively, the presence of normal magnetic fields could influence the distribution of certain types of dark matter. If a component of dark matter does have an ultra-weak electromagnetic charge, it could be subtly repelled or attracted by the magnetic fields of galaxies, creating slight, non-random distributions in the dark matter halos that might one day be inferred through meticulous gravitational mapping. While these ideas remain highly speculative and firmly in the realm of theoretical physics, they open a breathtaking new perspective. They suggest that the cosmic magnetic web we've been mapping might be even more complex and deeply rooted than we imagined, woven from threads both seen and unseen. The immense, powerful fields of magnetars and the vast, guiding fields of galaxies could be just one visible part of a far grander magnetic tapestry that connects the entire contents of the universe, both the light and the dark. It's a reminder that solving one cosmic mystery, like the origin of magnetic fields, might ultimately require us to solve another, the true nature of the dark universe that holds it all together. When we think of magnetic fields in our solar system, we naturally picture planets and the sun. But one of the most astonishing revelations of modern planetary science is that some moons, those seemingly passive satellites, are hiding their own magnetic power. The champion of this unexpected class of objects is Jupiter's moon Ganymede. Not only is it the largest moon in our solar system, even bigger than the planet Mercury, but it is the only moon we know of that generates its own magnetic field in much the same way a planet does, through a hidden, liquid iron dynamo deep within its core. This discovery fundamentally changed our understanding of what a moon could be, transforming Ganymede from a frozen, inert ball of rock and ice into a complex, dynamic world with a hidden, churning heart. The existence of this internal dynamo means Ganymede is not just a passenger within Jupiter's colossal magnetic fortress. It is an active participant carving out its own distinct space. As Ganymede orbits Jupiter, it plunges through the different regions of the gas giant's rotating magnetosphere. This creates an extraordinary and constantly shifting magnetic dance between the two bodies. For a few hours out of its 7-day orbit, Ganymede is in a unique position where its own internally generated magnetic field is aligned with Jupiter's in a way that allows them to connect directly. During this brief window, the magnetic field lines from Jupiter effectively plug directly into those of Ganymede, creating a temporary magnetic highway between the two worlds. This connection allows charged particles from Jupiter's magnetosphere to be funneled directly down onto Ganymede's polar regions, where they smash into the icy surface and create permanent, glowing auroral ovals around its north and south poles, much like those on Earth but embedded in ice rather than an atmosphere. For the rest of its orbit, this magnetic relationship is far more adversarial. As Ganymede moves, its intrinsic magnetic field acts like a shield, pushing against the overpowering flow of magnetized plasma from Jupiter. This creates a miniature magnetosphere within a magnetosphere, a protective magnetic bubble that stubbornly deflects the relentless onslaught of energetic particles from its parent planet. The Hubble Space Telescope has given us stunning visual evidence of this interaction by observing Ganymede's auroras. The rocking motion of these ultraviolet headlights, which do not stay fixed to the moon's poles but sway back and forth in response to the changing tug of Jupiter's magnetic field, provides a beautiful and direct confirmation of this complex magnetic interplay happening over 500 million miles away. This magnetic activity has profound implications that extend far beyond mere planetary science. Ganymede, along with other icy moons like Europa and Enceladus, is a prime candidate in the search for life beyond Earth. Astronomers are almost certain that Ganymede possesses a vast, global saltwater ocean hidden beneath its thick, icy crust, an ocean that may contain more water than all of Earth's oceans combined. The moon's internal dynamo and its resulting magnetic field may play a crucial role in making this subsurface environment potentially habitable. The magnetic shield provides a critical layer of defense, helping to protect the icy surface from the worst of Jupiter's brutal radiation, which could otherwise break down complex organic molecules that might exist there. Furthermore, the relentless magnetic friction between Ganymede and Jupiter, along with the tidal heating caused by Jupiter's gravity, likely provides a vital source of internal energy that helps keep that deep, dark ocean in a liquid state. This suggests that the conditions for life may not require a planet at all, but could thrive in the hidden oceans of a magnetically active moon, forever orbiting within the protective, if sometimes violent, embrace of a giant. But to truly grasp the entire history of our planet's dynamic magnetic field, we need a record that stretches back far beyond human instruments or even ancient pottery. We need a geological time capsule, a natural recorder that has been diligently logging magnetic data for billions of years. This incredible chronicle is written in stone, specifically in the volcanic rocks that form the very foundation of our planet's crust. It's a process that turns flowing, molten lava into a permanent, unflinching archive of our magnetic past, When volcanic rock, like basalt, first erupts onto the surface, it is incredibly hot, often exceeding 1000 degrees Celsius. At these extreme temperatures, the tiny magnetic minerals within the molten rock, primarily magnetite, are free to move and jostle. They are like countless microscopic compass needles that have been heated until they lose their magnetism, becoming disorganized and pointing in random directions. The magic happens as this lava flow begins to cool. As the temperature drops past a critical point known as the Curie temperature, which for magnetite is around 580 degrees Celsius, something remarkable occurs. At this precise moment, these tiny magnetic minerals regain their ability to become permanently magnetized, but they don't just choose a random direction. As they cool through this critical threshold, they align themselves perfectly with the direction and intensity of Earth's prevailing magnetic field at that exact location and moment in time. It's as if each mineral grain instantly freezes, capturing a snapshot of the planet's magnetic field. Once the rock has fully solidified, this magnetic signature is locked in place with incredible durability, preserving that specific magnetic north and field strength for millions or even billions of years, completely immune to any later changes in the Earth's field. This process provides scientists with a direct and unambiguous read on what the magnetic field was doing when that rock cooled. This natural recording system is the very foundation of the science of paleomagnetism, and its most powerful application has been in proving the theory of plate tectonics. By taking core samples from ancient volcanic rock formations around the world and carefully measuring their locked-in magnetic direction, researchers can determine their paleomagnetic pole, essentially where the magnetic North Pole was relative to that rock when it formed. What they discovered was astonishing. When they analyzed rocks of different ages from the same continent, they found that the apparent position of the North Pole seemed to wander dramatically over geological time. A 200-million-year-old rock in Europe might point to a North Pole in a completely different location than a 50-million-year-old rock from the same spot. For a while, scientists entertained the idea that the magnetic poles themselves were wildly migrating across the globe. The true explanation, however, was far more revolutionary. The poles weren't wandering, the continents were moving. This apparent polar wander path was actually a record of the continent's own journey across the Earth's surface, rotating and drifting over millions of years. When this data was gathered from all the continents, the pieces of the puzzle clicked into place. The individual wander paths for South America and Africa, for instance, were completely different until you digitally closed the Atlantic Ocean and pushed the continents back together. Suddenly, their separate polar wander paths merged into one coherent, logical track, providing irrefutable evidence that these landmasses were once joined in the supercontinent Pangaea before drifting apart. The magnetic memory in the rocks didn't just tell us about the field's history, it drew the map of our planet's deep past, revealing the slow, majestic dance of the continents. Beyond tracing continental drift, this rock-bound archive has also preserved the history of the magnetic field's more erratic behavior, its reversals. As new oceanic crust is formed at mid-ocean ridges by volcanic activity, it faithfully records the magnetic field's polarity as it cools. This creates a symmetrical magnetic barcode on either side of the ridge. Ships towing magnetometers across the oceans discovered these alternating bands of normal and reversed polarity stretching away from the ridges, providing a precise timeline of hundreds of reversals stretching back nearly 200 million years. By combining this magnetic seafloor data with isotopic dating of volcanic rocks on land, scientists have constructed a detailed calendar of these flips, known as the geomagnetic polarity timescale. This allows them to not only date the age of the ocean floor, but also to correlate geological events across the globe with incredible precision. A layer of volcanic ash in Italy that recorded a reversal can be instantly linked to a lava flow in Colorado that recorded the same reversal, creating a global timeline of Earth's history written in the magnetic memory of its stones. These silent, steadfast rocks have become the most reliable historians of our planet's deepest secrets, offering a continuous narrative of a shifting magnetic field and a world in constant, slow motion. But to push our understanding of magnetism to its ultimate limit, we must venture beyond observable matter and energy and into the very fabric of nothingness itself. We arrive at one of the most mind-bending frontiers of theoretical physics, where extreme magnetic fields interact with the quantum vacuum. We often think of empty space as a true void, a complete nothingness. But quantum mechanics paints a very different picture. What we perceive as a vacuum is actually a seething, bubbling froth of fundamental activity. According to the rules of quantum field theory, pairs of virtual particles and antiparticles are constantly flashing into and out of existence, borrowing energy from the vacuum for an immeasurably brief moment before annihilating each other and paying that energy back. This isn't just a mathematical quirk, it's a fundamental property of reality, and it means that so-called empty space is actually brimming with transient energy. Now imagine imposing the most powerful magnetic field in the universe onto this quantum foam. The field begins to exert its influence on these virtual particles. Because they are, for their fleeting existence, real particles with charge, they are affected by magnetic forces. A sufficiently powerful field can actually polarize the vacuum, influencing the behavior of these virtual pairs. It can stretch the orbits of virtual electrons and positrons, and even lower the energy required for them to become real. This leads to a staggering theoretical possibility. In the presence of an ultra-strong magnetic field, the vacuum itself can become unstable. The field can effectively boil the vacuum, providing the necessary energy for these virtual pairs to become real particles, pulling them out of nothingness and into permanent existence. This is not mere science fiction. It's a direct prediction of quantum electrodynamics, suggesting that a magnetar's field could literally tear particles from the fabric of space-time. The most dramatic prediction of this effect is something called vacuum birefringence. In ordinary space, light travels straight, and a vacuum has no preferred direction. But a powerful magnetic field breaks this symmetry, giving space a distinct directionality. This polarized vacuum then affects light traveling through it. Photons vibrating parallel to the magnetic field will interact with the virtual particles slightly differently than photons vibrating perpendicular to it. This means they will travel at very slightly different speeds. A vacuum in a magnetic field effectively becomes like a crystal, a phenomenon known as birefringence. This would cause the polarization of light passing near a magnetar to rotate in a specific, measurable way. And in a monumental breakthrough, astronomers using the European Southern Observatory's Very Large Telescope did exactly that. By studying the polarized light from the neutron star 1E 1207, 5209, they detected the signature of vacuum birefringence for the very first time, providing direct observational evidence that a magnetic field can indeed alter the fundamental properties of the void. This discovery opens a window into physics that we can never hope to recreate in a laboratory. It confirms that in the most extreme environments, the lines between something and nothing begin to blur. The magnetic field ceases to be just a force acting on particles. It becomes a tool for manipulating the underlying quantum stage upon which the drama of the universe plays out. It suggests that the vacuum is not an empty container but an active participant in physics, a medium whose properties can be changed by the immense forces at work in the cosmos. This profound connection between the largest magnetic structures and the smallest quantum fluctuations reminds us that to fully understand the universe's most powerful magnets, we must also comprehend the nature of nothing itself. And as our journey through these 30 astonishing facts about the universe's magnetic extremes draws to a close, we find ourselves not at an ending but at the threshold of a new era of discovery. The cosmic magnetic mysteries we've unraveled so far are merely the prelude to an even grander story waiting to be told, one that will be revealed by a new generation of telescopes and missions specifically designed to probe these invisible forces with unprecedented clarity. Leading this charge is the Revolutionary Square Kilometre Array, or SKA, a project so ambitious it redefines the scale of astronomical observation. Unlike a single dish, the SKA will be a vast network of thousands of radio antennae spread across 2 continents, in South Africa and Australia, working in perfect harmony to create a collective collecting area of, as the name implies, roughly 1 square kilometre. This colossal instrument will be so sensitive it could detect an airport radar on a planet tens of light years away. But its true power for our story lies in its ability to map cosmic magnetic fields in exquisite detail. The SKA will achieve this by becoming the ultimate synchrotron radiation detective. Remember, when high-energy electrons spiral around magnetic field lines, they emit this distinct polarized radio glow. The SKA's incredible sensitivity will allow it to detect this faint signal from the very earliest epochs of the universe, tracing the magnetic web not just within nearby galaxies, but across the vast cosmic voids and deep into the ancient past. It will map the field structure in the first galaxies to ever form, potentially revealing how those initial, weak seed fields were first amplified. It will probe the magnetic environment around protoplanetary disks, showing us how magnetism guides the birth of new solar systems. And by observing the polarized light from countless distant pulsars, the SKA will act as a giant interferometer to detect and measure the long-theorized cosmic gravitational wave background, using the precise timing of these cosmic lighthouses as they are subtly stretched and squeezed by ripples in spacetime. This one instrument will simultaneously explore the universe's largest magnetic structures and its most fundamental physics, but the revolution doesn't stop on the ground. Advanced space observatories will complement these ground-based behemoths, free from the distorting filter of Earth's atmosphere. Missions focused on X-ray and gamma-ray polarimetry are poised to open an entirely new window onto the most violent magnetic domain. For decades, we've studied objects like magnetars and black hole jets by analyzing the intensity and spectrum of their high-energy light. The next step is to measure the polarization of this light. The degree and angle of polarization in an X-ray beam coming from near a black hole's event horizon or a magnetar's surface carries encoded information about the geometry and strength of the magnetic fields in those regions, details that are completely lost in a simple intensity measurement. New missions equipped with cutting-edge polarimeters will, for the first time, allow us to literally map the magnetic field structure in the inner accretion disk of a black hole or right at the surface of a neutron star, testing our theories of gravity and matter under extreme conditions in ways we've never before been able to. These technological leaps will undoubtedly lead us to new magnetic mysteries that we cannot even yet conceive. They might finally allow us to detect the faint radio whisper of an exoplanetary magnetic field, confirming the existence of another protected, Earth-like world. They could reveal the role of magnetism in the mysterious fast radio bursts that occasionally pulse from across the cosmos. Or they might even uncover evidence for those primordial magnetic fields from the universe's first second, providing a crucial clue to the conditions present at the birth of everything. The study of cosmic magnetism is moving from noting its existence to truly understanding its intricate role in the cosmic narrative, from the formation of the largest structures to the stability of the smallest planets. With these new tools, we are not just building bigger telescopes, we are forging the keys to unlock a deeper layer of reality, ready to illuminate the dark, magnetic skeleton of the cosmos and reveal the full, magnificent power of the universe's most extreme fields. From the gentle field that cradles our planet and guides a wandering bird, to the cosmic dynamos deep within stars and the frantic hearts of dying galaxies, we have journeyed across a universe invisibly woven with magnetic force. We have stood in awe of stellar corpses with fields so strong they twist atoms into cigars, witnessed black holes that fired jets of energy across millions of light years, and learned how the humble alignment of dust grains paints the magnificent nebulae that grace our telescopes. This exploration reveals a profound truth. Magnetism is not merely a side effect of the cosmos, it is a primary architect. It regulates the birth of stars, guides the formation of planets, accelerates the most energetic particles in existence, and protects the delicate conditions that allow life to arise and persist. Our place in this magnetic cosmos is both humbling and empowering. We are the beneficiaries of a planetary shield that has stood guard for billions of years, and we are the consciousness that has evolved to perceive, measure, and finally begin to understand these invisible forces that shape everything. The same fundamental physics that creates the aurora dancing over our poles also powers the fury of a magnetar flare seen across the galaxy, connecting us through universal laws to the most extreme environments imaginable. This journey through 30 facts is just the beginning. Every new telescope, every novel experiment, and every daring theory peels back another layer, revealing a cosmos more intricate and magnificent than we ever dreamed. Now, we want to hear from you. Which of these magnetic marvels captured your imagination the most? Was it the idea of a pulsar's perfect cosmic clock, the terrifying power of a magnetar, or perhaps the humble bacteria with their built-in compasses? Share your favorite magnetic fact down in the comments and let's continue the conversation. If you enjoyed unraveling these mysteries with us, make sure to subscribe and hit the bell so you don't miss our next journey into the wonders of space. The universe is full of secrets waiting to be discovered, and we can't wait to explore them with you.